electrical energy. All right. We're going to go back to our story from before where we compared the force of gravity and the electrical force between two objects. If you recall, the force of gravity is based on masses, and we had this equation based on the masses and the distance between them, the r on the bottom. And of course the gravitational constant, which just sort of, essentially what the constant does is it turns everything into the proper units. It allows us to use our standard units and then come up with answers that will also be in standard units. And so depending on which units you use, you can have different constants. But since we always use the standards, we get these standard constants like the capital G for gravitation. Then we discovered that the electrical force between two objects has its own constant, K, 9 times 10 to the 9, and it's based not on mass, but on charge, which we use Q1 and Q2, and again, the square of the distance between them. So these two equations were very similar and worked very much the same way because they describe the same sort of situation. In both of these cases, if you have an object and another object, there was an attraction, which means this object would feel a force towards the other object. And it wouldn't matter where it was, that r, the reason we use r is because it's a radius, right? Anywhere around here, all of these objects, which are about the same distance away in a radius of this circle, would experience the same amount of force. And they would all be pulled in towards this object. And so what we describe is a force field. A field is the region of space around an object. And so for an object with a particular mass m, if you were to drop any other mass around it, those masses would all feel forces in this direction. So we can describe the field around a mass as this. This would be the gravitational field. And then if we look at the electrical force, we see it's the same idea. If you have an object with a positive charge here, well, let me change that. Let me make that a negative charge, so it parallels gravity. Okay. Then, whoops, what happened there? Erase. There we go. Okay. Then, if you take another object here, if this is a negatively charged object, then if you take a positive object with positive charge, it will be attracted to this other object. And of course, it'll feel a force inward. And it doesn't matter where in this circle you put it, as long as it's the same radius away, right? That positive charge will feel a pull or a force of attraction towards this other object. And of course, this forms a circle with a radius. So it's the same picture. And what that means is essentially, if you have an object that is a negatively charged object, then around it, all positive charges would be attracted to it. And you can see how these pictures look the same. And that's because although they work on different properties, the fields of gravity and electricity are very similar. In fact, they're identical almost. But there is one key difference, and that is with gravity, there's only mass. Right? And because there's only one form of mass, in other words, there's no different kinds of mass, there's just mass. And so what happens is all mass is attractive, and so these fields are only attractive. They only cause things to force together, to be pushed together. There's no repulsive pushing away. But with electricity, there are two kinds of charge. And of course, we call them positive and negative. And so that means that it's possible to have attractive forces, but it's also possible to have repulsive forces. And so if we were to draw the very same picture with gravity, there's no other picture to draw. There's a mass in the middle, and these masses are attracted to it. But with the forces, I could change this charge in the middle to a positive charge. So if I put a positive charge in the middle, then another positive charge feels repelled. And so we get a field that looks similar, but the arrows are all in the opposite directions. So positive charges all around this circle would be pushed away. And this repulsive force exists with electricity, but not with gravity. And it's simply because there are two kinds of charge, whereas there's only one kind of mass, as far as we know. Now, interestingly enough, scientists are on the verge of looking at something called we've known about antimatter, which is sort of an oppositely charged mass. But what changes with antimatter is the actual electrical charge. So it's not really a different kind of mass. It's another kind of electrical charge. And that fits in with our plus and minus. We also are studying things called dark matter, and there's a lot of stuff that we don't know about matter as of yet. So it might come to pass that there are situations where we could find a repulsive form of gravity. But for now, and especially when we're just beginning to understand gravity, we're just going to understand it as much as we know to this date, which is that gravity is primarily attractive. Okay, so that's all about the forces, and we know all that, and we get it. Now, let's draw a comparison. What we said before, and I'm just going to do this in a sort of a simplified manner, is that remember that energy, right? Energy is equal to work done. Well, I should say a change in energy means that work is done. And when we talked about gravity, work, of course, is force times distance. So when we talked about gravity, if we talk about that center, I'll just draw it larger. If we talked about that center mass in the middle and another mass, say here, then we could say that in order to move this mass higher away, okay, because there is a force of attraction that we have to sort of, this is the gravity force, we would have to have an applied force in the opposite direction to lift this object up. So what we're essentially doing is we're moving the object to a different position in the field, right? The field depends on the radius. Remember, we drew our pictures. So instead of having a radius this far away, we've moved it out further to a different position. That's a different R. And that changes, of course, the value of the force. Well, because we're moving this a certain distance, then what we're essentially doing is we are applying a force through a distance right here. In other words, we're doing work when we lift something up. And why are we doing work? Because we are changing its position in the field. And when we change its position in the field, we are changing what's called its gravitational energy. And we describe this by looking at, well, the complicated way of doing it was to take the force equation for gravity. And we use this process because force times distance on a force distance graph, a force displacement graph creates a shape, right? And it's the area under this graph that represents the work done. We can do areas for simple things like rectangles and triangles, but unfortunately in the real world, not everything is a rectangle or a triangle. So what's happened, of course, is this invention of calculus. And calculus has a sort of a process called integration, and some of you might even know about it now, integration, which basically allows us to calculate areas underneath particular graphs. So we could calculate this area by integrating. We're not going to learn how to integrate because that's a whole course of calculus. But through the process of magic of calculus, I guess you could call it, we turn this into, whoops, I have to rewrite that, sorry. We turn this into an equation which represents the energy Okay? So you can think about integration as a way of taking this force and finding the area under the force and the r, so the distance r. You'd have a graph with the force of gravity here and the r here, which is a distance. And of course, you'd find the area by doing this integration process. And we found that the gravitational energy was negative gm1 m2 over just r, not squared. So it's kind of complicated. You've got to be careful not to confuse them. Well, guess what? We can do the exact same process with the force, the electric force. And we can get the K, Q1, Q2 over R squared. And we can use the magic of integration on this, which will do the very same thing. And when it does, it will tell us what the electrical energy should be. And here's what it comes out to. It comes out to K, Q1, Q2 over R. But there's a very slight difference. With gravity, this always comes out to a negative number because these masses only have one option. They both have to be positive numbers. But it's possible that these charges right here could be a plus or a minus, which means that when you integrate this, you could end up with a plus or a minus answer for your integration. And so electrical energy has a slightly more complicated problem. It's not always going to be a minus or a plus. And the reason, again, is because charges can be positive or negative. If you had two positive charges, this would come out to a negative, just like it did up here with two positive masses. And if you had two negative charges, those two negative charges would would give you a positive number, which would then integrate into a negative number as well. But if you had one of each, the case of a plus and a minus, the case of a plus and a minus gives you a negative answer, which then when you integrate produces another negative, which causes the whole thing to be positive. And so we see that when you have two positives or two negatives, you get the same answer. And that's because these are both representing repulsion in the field, the force field, but the opposite is the one, whoops, I meant to write a plus and a minus there. The opposite, can't write with an eraser, there we go. So the opposite one, the plus and the minus, is the one that gives us attraction. And so we were in the habit of using, when we calculated electrical force, we knew that if we calculated this and we got a positive answer for the force, that would be like these two situations right here, and it would be a repulsive situation. But if we had a negative and a positive right here for our Q's, then it would produce this, or an attraction. Now, what does this mean in terms of energy? Well, you'll recall that when we did the gravitational energy for gravity, right, e.g., we described gravity as an energy well, where the zero was sort of here, the flat sort of space. And the mass here creates this energy well. And what that means is you have to add energy to get away. Right? Because gravity is attracting, if you try to go this way, the gravity is pulling you back. You need to apply a force. You don't need to apply a force to move this way. Things will just automatically fall towards something. So we don't need to apply a force or change our or add energy or do work. Where we do the work and add the energy is on the way up as we lift or push things away. And that means that this represents a very large negative value. If you think about this as being on an axis, right? This is your zero line, this x-axis. So a mass distorts the space around it and creates a large negative energy, which then you must add to. So when you add negative energy, you move you move up this scale. Well, when you get to, say, here, you're still at a negative number. And if you add all of the energy necessary to get completely away from this object, enough to push the object out of the well so that it reaches the zero level, it then feels no more attraction to the object, and it's basically at zero level, and it's just going to be floating free with no more interaction. Now, of course, that's an infinite situation, but for our purposes, somewhere around here, there's a reasonable spot where it's near zero, and that's when, if you threw a ball away from the Earth, and you gave it so much speed, in other words, kinetic energy, right? You added energy to it by giving it speed, it could get all the way out, and eventually it would just keep on going and never come back to the Earth. So it's escaped, we call it. Remember the escape velocity. And so we talk about the energy well when we talk about gravity, because gravity only has one option. Well, this is exactly the same case when we look at a negative object causing an electrical energy well, and we describe what happens with a positive object. In other words, and it could be the other way around. It could be a negative object up here and a positive object in the middle. Basically, we just have to have opposite charges, right? A positive and a negative. And this is where we have the attraction. This is where it mimics gravity. It works like gravity. And this is exactly the same. This would be a negative energy well. This would be the zero. And you would have to push on this charge to get it to go away from the negative. You'd have to apply a force, which means you're pushing it, this distance, which means further away, right? Which means you're doing work, which means you're changing its energy. But it's also possible to look at an energy hill. And this is kind of the case where you have a positive object here at the bottom of your hill and a positive object. If I had a positive object here, I would not have to push it for it to escape from this well. It would automatically repel and want to move away. What I would have to do is I would have to add energy to bring it closer to the object, right? So in this case, you have two objects, a negative and a positive, and if you want them to move away from each other, you have to add energy or do work. Here, if you have, this was going to be a positive and a positive, well, then you don't add energy for them to move away. You add energy to make them get closer. And so here we have a situation where this formula may or may not have a negative number right here. And so again, what we have to do is kind of the trick we did with forces. Now, remember that energy is not a vector. And so the quantity of the energy, right, is not a directional thing, the plus or minus. When we're talking about gravity, this negative doesn't mean it's down. What this means, right, is that there's an attraction. It means attraction or repulsion. And so here, all we're doing is remembering that we could have both, and we have to rely on the context to understand which way things would go. All right. So essentially, what do we have here? We have a new equation, and that is that electrical energy can be found by using K, Q1, Q2, and R. And this value could be a positive or a negative, which would mean you would have to add or subtract energy depending on your situation. Okay, so we could write plus or minus here if we wanted. And you have to think of that. So you have to just imagine the picture that I drew. If you're trying to push two similar charges together, you would have to add energy. They would naturally pull apart. But if you're trying to push two opposite charges together, you don't have to push. They will naturally push. So you have to add your energy in trying to pull them apart. So that's what the difference means. So now you can figure out, as a quick example, we can figure out how much energy there is between two objects. Just like we can figure out the energy of an object, say here, if this is the Earth and this is the height of an object, we can figure out its energy by doing G, M1, M2 over R. And it will always be negative for gravity, so we put the negative in. But if this is a negative charge here, and this is a positive charge here, we can figure out the energy associated with its position by doing K Q1, Q2 over R squared. In this case, it will become a negative number. But if this was a positive charge, this would become a positive number. And so we get both options. Now, when we move things above and below the Earth, because with gravity, we have this magical spot. We have this radius of the Earth, and we call this the Earth's surface. And that's where all of our action happens, right? So what we were able to do is we were able to modify the energy equation. Well, actually, what we modified is the force equation. Let me write the force equation. G m1 m2 over r squared. And we look at these three numbers and turn them into a little constant g, because they never change if you stay on the Earth's surface, and we got a little mg as a shortcut for gravity. I wonder if the same is possible with electricity. Well, it turns out that it is. However, when you talk about the Earth, we have this surface, right, where we live, which is a convenient spot, sort of somewhere between the center and the object. It's a spot. Remember, all these R's are measured from the center of the Earth. And so this little spot right here that we're standing on happens to be a little bit in between. And it was kind of a pain because we always had to subtract it or add the radius of the Earth. There is no convenient spot when you're talking about charges. Here's a plus charge, here's a negative charge. Well, there's no surface here that things could stand on. And so the shortcut for electricity may or may not always be as useful, because there is no surface somewhere partway in between. It just doesn't exist. But there is a shortcut, and what it turns out to be is it turns out to be a matter of perspective. So if we take an object like this, well, let me do both together. It's easier if I do both, because then I'll do the gravity over here in red. If we take the force of gravity between two objects, G m1 m2 over r squared, right? Then what we can do is we can take these numbers and turn them into a little g and get Fg equals mg. Now, what exactly does this mean? What this means is that little g stands for, here's the center of the Earth. We'll put the surface here. What it means is this mass of the Earth is creating a field. And this g is the indicator of the field strength at precisely one radius away, the surface of the Earth. The problem is if you move away, this little g changes, because the r changes in this equation. So little g is useless anywhere except on the surface. Okay. But it is handy because we tend to live there all the time. Okay, let's cross over here to the other side, and let's do a parallel with the energy or the electrical force first. K Q1 Q2 over r squared. Now here's the catch. What made this simple was the mass of the Earth. Remember, the Earth's mass here never changed. When you're talking about two charged objects, there's no guarantee that either one of these Q's is going to always be the same. So again, we lose that sort of special situation of the Earth. This Q1 could be anything. It's not always going to be Q1, right? And so what we have here is the same numbers, but they're just not always going to be the same. They're not always going to work out to say 9.8, because Q1 could be anything. You see the difference? But that doesn't mean we can't calculate it. We can still calculate a value for this. And just like over here, these three numbers turned into the little g, which is called the gravitational field constant. The gravitational field constant, g. We can get what's called the electric field constant. Or sometimes we use the word strength, the electric field strength. And over here, this could be the gravitational field strength. That's a word we often use instead of constant. And what would it be? Well, we'll have to call it something. We can't call it little g, but if we take those same three numbers and multiply them, what we're going to call it is the electric field strength, which I like to use a scripted E, like this. The electric field represents K, the Q1, and the R squared. And it leaves out the Q2, sort of by itself, separate. And guess what? Just like the force of gravity, then, you can take that little g and multiply it by any mass, right? This mass is actually the mass over here that was left out. It's the mass of the object. And so here we can call this E, and we can say that the force electrical is the constant E. Whoops, hang on, eraser here. Is the same thing. We can take a particular Q, which would be the charge over here, any charge, and we could put an E here. And that would be the formula or the shortcut for doing electrical energy. But unfortunately, it's a little more complicated than gravity because gravity makes more sense to us. So we need to pull apart what this actually means right here. And what it means is that if you want to go a very particular distance away, let's pick a distance. This G means that's how strong gravity would be at any particular R away. Now, it's 9.8 at the Earth's surface, but it could be 10.7 if you went deep into the Earth, say somewhere like that. Or it could be, 6.4 if you decided to go way far away from the Earth. But of course, we never do because the surface is the only place that matters. So these other numbers don't really mean much to us. But what we can consider, though, is we could consider that if G is the force field, or the field strength, G is being created by Earth. Oh, I got my eraser on. G is being created by Earth, right? Over here, these numbers are all about, this was Earth's mass right here. So G is actually the field created by Earth. So when we use Fg equals mg, we're talking about how the field created by Earth affects a mass placed in that field. Okay, in that field. And so we say, here's the Earth. There it is. And it's got a field all around it. Here, we'll draw the field lines, right? Any mass is going to be attracted like this. Now, I could place a mass here. Boom. And I could calculate, the G represents the strength of the Earth's field. And then I could calculate the force that's required, the gravitational force, if I take that mass and multiply it by the G, the field strength. Now, the G will be 9.8 if I go precisely here on the Earth's surface, but it will be any number anywhere else in the field. But I could still calculate it. I calculate it by changing the R value, right? So I can still use other values of G for far away. Likewise, if we have a charge, let's say we have a negative charge here. Well, let's put keep it like gravity, a negative charge right here. We're going to call this QM, which stands for the master charge. It's the one making a field, so it makes a field around it. The field is there no matter what. And then let's say I take a little charge of positive and I stick it here, a certain R distance away. Well, I could figure out what the strength of the field would be at that distance, right? That would be some number. And then I could figure out the force, the electrical force needed that would be felt by that positive charge by taking that positive charge. And we're going to call this positive charge the test charge. That's what his name is. So QT. And multiply it by Q, the field strength. So over here, Earth is the master mass, and little things that are falling around the Earth or placed on its surface like trucks and cars and people, these are what we call the test masses. They're the things we drop into the field made by the Earth. And here, the test charge are the little charges that we drop into the field made by the center charge or the master charge. So basically, what this does is it tells you the force from the perspective of the master charge. It's all about this master charge. Whereas this equation doesn't really give us the force with respect to this charge at all. It doesn't really depend on that charge. It's another way of calculating the force from the perspective of the two charges together. But they really are the same thing because remember, all of this is just the E, and the QT is the same as that. So it's just a matter of perspective. So if you're doing force from the perspective of a master charge or a single charge, and you want to know how other things would be affected by it, you can calculate their force using Fe equals QE. Now you'll have to calculate E. The problem is, with gravity, we had G near the surface. It was always 9.8, but E can be any number. So it has to be calculated. And the way, of course, you calculate E is K, QM, the master charge, over R squared. That's the fields. And we've already talked about electrical fields, and so that's what we should have that sort of under our belt. Now, we get to energy. Okay, so now we have the energy equation for electricity, K Q1 Q2 over R. And when we were doing our parallel for gravity, if we had the force of gravity equals mg, then we could do the force of gravity, or the energy of gravity, equals mg multiplied by h, by the change. That's a force times a distance, right? Now, technically, it's mg times the change in height, h2 minus h1. But h1 is usually considered a 0 as long as we're using little g at the surface and we had the shortcut, right? But with electricity, we don't have that convenience. So this form is a little bit easier to make the comparison by. All right. So what happens then if we take the electrical force? So here's a charged object, and we're going to try and lift this negative object. So if we lift it, we've applied a force, and that force would be an electrical force, right? QE. And we would have to move it a certain distance. Well, the distance that we're moving it is an R. We're changing the R. All right. So now, just like mgh, let's call this the distance, what we move it, d. We can use the electrical energy, which is the work done, and we can say it's the work done by applying the electrical force, which is QE, and moving it a certain distance, QED. So we have another little kind of shortcut formula. We can actually calculate how much work is done in moving things from one point to another in an electrical field. Now here's the catch. This E has to be constant for this to work. And of course, it wouldn't be constant if you were just moving two charges away from each other. So the only time this QED could work is if you have a constant situation, a constant E situation. And we're going to get to how we generate constant electrical fields, but perhaps we'll save this for another sort of lesson. All right, so far, all we really have to worry about is our new formula, electrical energy, KQ1, Q2 over R. And this energy could be positive or negative, which basically means it's either added or subtracted, depending on whether you're trying to move two similar charges or two opposite charges. And then it's pretty much plug and play, right? It's pretty much plug and play. So I'm going to give you some questions to work on, and then in the next video I'll come back to this part and this constant E, and I'll show you how we can generate situations where the field strength is constant, sort of similar to, you know, the Earth's surface being always the same. All right, so for now we're just going to practice with this equation and see where we